Today I want to talk about telomeres and Sam Walton. This was Sam Walton in 1977. He was 59 years old and there were 177 Walmart stores. And with 177 stores, he was rich. He probably was worth tens of millions of dollars in 1977. And this is him again, and nobody's sure exactly what year this is, but the best estimate I saw was around 1985 when there were 800 Walmart stores. So by the time this photo was taken, he was a billionaire. He got there sometime in his 60s. So on here, the chromosomes are in blue, and you can see there's little red parts on the end, and those red parts are telomeres. And the way that telomere works is when a cell divides, all the chromosomes have to be replicated. And as the proteins that replicate these chromosomes go along the DNA, they eventually come to this bundle of DNA at the end that doesn't really code for anything. But when those proteins get to the very end of that telomere, they cut it off. So after the replication is done, the telomere is actually shorter than it was before the replication started. And for a long time, it was thought that this is basically what causes aging. You run out of telomeres on different chromosomes, and at that point, those cells can no longer replicate. And as cells become damaged, if nothing around them can replicate to replace them, then the body's cells age out and die. And what all that kind of implied is the length of your life really is decided at your birth. You only have so much telomere on each chromosome, and when it's gone, it's gone. And then your body's just going to kind of run out and eventually die. Well, that isn't really thought to be the case anymore. And this study looked at how telomeres are lengthened out over the course of someone's lifetime. This set of proteins here makes a little machine called Telomeres. And what Telomeres does is it adds randomly to the length of each of those telomeres. So even though it gets clipped off at replication, it gets added back to later on. Of course, if you're extremely ill or going through a lot of physical damage, there isn't necessarily enough time for telomerase to add back onto the end of the telomeres. So at that point, the telomeres start shortening. So it makes sense that if somebody has long telomeres at birth, they're going to be more able to overcome injuries or severe illnesses that keep happening to their body. The other side of it, though, is those cells can all replicate more quickly. So if you develop cancer cells, there's not going to be anything to slow them down from replicating out of control, and you can wind up with cancer that spreads very fast. So that's the trade-off. You kind of got to put a limit on how much cells can divide, or cancer can take the life of the body early. So what researchers did was they took a group of 147 individuals that they had basically a whole lot of data over the course of their lives on, including cord blood. And what they did was they looked at the lengths of different sets of telomeres, and this is actually going to be an average length, and it's based on kilobases, so thousands of DNA bases that were in that telomere. And you can see that you basically wherever people started was kind of where they ended. People who started with short telomeres basically kept short telomeres their whole life. Now, in red, you can see it's labeled IPF. That's for Idiopathic Pulmonary Fibrosis. And that's a disease that basically causes thickening of the tissues in the lungs alveoli. So that's a chronic condition that causes a lot of damage over the course of someone's life. Anyway, the folks who had IPF had consistently shorter telomeres than folks who had generally been healthy their whole lives. And here's a little bit better of a depiction, in my opinion. This is just for the healthy group. And basically, they found that folks who started out with long telomeres, those telomeres tended to shorten over the course of their life. But the people with the shortest telomeres, their bodies just kept adding to them as they aged. So if telomere length isn't such a great way to look at cellular aging, maybe epigenetics and DNA damage are a better way. So epigenetics is just, the DNA gets unwound and, wound up around kind of these cylindrical proteins. It gets unwound, used, transcribed, but it doesn't always get put away the way it should. In addition, there are things like radiation, sunburns, toxins, alcohol, cigarettes, garbage in our food that can actually damage the DNA. And that DNA damage, while a lot of it can be repaired, it isn't always. So another way to look at cellular aging right now is to take a look at the accumulation of all those changes, all the variability within that DNA, and put it along a curve. So you take the DNA mutations and you take the epigenetic activation, you plot it all along the curve, and as someone ages, this curve should flatten out. So you should have less height and it should get lower, and there should be more of a spread of what's activated and what's been mutated. As cells age, they lose their ability to do their jobs. And when a cell can no longer do anything but sit there and eat, that's when it's called a senescent cell. It's basically a zombie cell. It's the living dead. It doesn't do anything. It just consumes. It doesn't do a job. So senescent cells cause trouble in a couple ways. The first way is that different genes within them can become activated and they can become cancerous. The other way is those senescent cells, for example, if you have senescent liver cells that are just sitting there and not doing anything, then they get in the way of the rest of the organ doing what it's supposed to do. Part of what the cells in our body naturally do is any proteins they're producing, they push some of them out to the edge of the cell membrane. And then cells from our immune system are able to recognize those different proteins. And that's part of the way that if a cell becomes infected with a virus, some of those viral proteins will wind up on the outside of that cell. And then an immune cell can come along, notice those proteins, and give the cell a command to apoptose, to basically do itself in. And ideally, it works that way with cancer cells and senescent cells too. And if the cell refuses to do what it's supposed to, then these things will gang up too and take it out. Well, here's a question. What happens, though, if it's the immune cells themselves that become senescent? What if the immune cells quit working? Well, a lot of the studies I'm seeing about aging right now are actually focused on the immune system. Basically, the idea is the immune system ages, and that allows the rest of the body to age. So there's all kinds of stuff being studied to look at how the immune system can be rejuvenated. So the idea is to wake back up blood stem cells and get them to produce new cells for the immune system, or to restore function within the thymus, which is basically where new immune cells are trained. But the reality is we're a long way off from that. And even if sometime in the future aging can be overcome, there's still going to be accidents, things will still happen, and eventually we all come to an end. Which brings me back to Sam Walton. This is 1992. There were 1,800 Walmart stores, and he was given the Presidential Medal of Freedom. It was an election year. And at the time, he regretted all the time he didn't spend with his family, with his wife, with his friends. Sam Walton's last words were, "I blew it. Make sure they're not yours."